Hello, and welcome to Space Environment Simulation Testing and Measurement, an EMA 2025 Expo event. My name is Matt Colding, and I'll be your host for today's presentation. Today's session will consist of two presenters, each with a Q&A portion. Please be advised that to submit any questions that you have during today's webinar, you should use the Teams Q&A feature. After each presentation, we will address any submitted questions. Should there be any unanswered questions at the end of the webinar, we will address them over email. Our first speaker today is Brian Wood. Brian received his master's degree in physics from Utah State University in 2015, where his research focused on the synthesis and optical characterization of carbon nanotube forests. After graduation, he worked at Space Dynamics Lab to help develop a neutral particle beam emitter to help simulate atomic oxygen ablation processes in low Earth orbits. He later returned to Utah State to join the material physics group within the physics department to research issues pertinent to the spacecraft charging community. He collaborated and authored studies involving the radiation effects of both spaceborne passive materials and powered components to understand how ionizing radiation and total dose affected their performance and material properties. Brian joined the EMA team as a scientist in 2020, where his main focus was the construction and development of the Space Environment and Radiation Effects, or SERI lab, which has been used to both validate EMA simulation software as well as provide commercial availability of measurements and observations applicable for space applications. Without further delay, I give you Brian.
Thank you, Matt, for the introduction. Like Matt said, we have two speakers today. The session is basically going to discuss two of the major areas of concern pertaining to spacecraft's interaction with the plasma environment. I'm going to focus more on the spacecraft charging portion and the ESD investigation, and that will be followed up by Mike Campola, who will handle the single event effects, sort of the rad-hard aspect. So spacecraft charging. So the space environment, is a pretty broad range of energies and varying fluxes, and also of particle species. Spacecraft charging, as it sounds, is basically how the spacecraft reacts to the buildup of charge from these energetic particles. And since we're concerned mostly with the higher flux, that is usually pertaining to the electron portion of that environment and the sort of lower energy range of that. So this plot kind of highlights that, where it's showing the differential flux of sort of the transit environment. And so at 1 keV, you can see that we've got 10 to the 11 particles here. And you only have to go to 100 keV to drop almost 3 orders in magnitude. And then by the time you get to 1 MeV, it drops pretty much 5 orders of magnitude. And so this is sort of the energy range that spacecraft charging is pertained to because of that higher flux. And it really is just this current balance between the spacecraft and the environment that's really dictating how the spacecraft charges. And so there's sort of two regions of spacecraft charging. There's surface charging and internal charging, which again are somewhat delineated by the energies of the incoming particles. Surface charging, the depth of the penetration is only going maybe tens of microns or so. Internal charging is going deeper than that, so it can produce deep dielectric charging, or it could penetrate sort of superficial shielding and sort of then allow surface charging of any underlying dielectrics. And so what are we concerned with here? It's basically, this charging, differential charging. That differential charging is producing, electrostatic discharges. These ESDs, they are always going to occur. The real big question is, do they damage sensitive components? Do they couple to electronics? And does this repeated arcing behavior produce any degradation? And so Here's a list of just some of the common areas of concern for differential charging. Uh, of course, there's the scientific instrumentation that the payload could carry. And so this could be optical lenses and mirror coatings that could be sensitive to ESD. You have communications, RF antennas that are exposed to the environment. They could have repeated ESDs that could couple to the electronics of the transceivers, or it could also produce ablation of any coatings that are on the antennas themselves. You've got, plasma probes or any other measurement device that essentially shift with depending on the charging level of the chassis of the spacecraft. You've got thermal insulations. These are usually multi-layered insulations, and so you kind of have these stacks of dielectrics and metallized dielectrics, and they kind of behave uniquely to charge buildup and discharge. Any exposed dielectric, triple junction points are basically going to be the primary arc site for differential charging. And by triple junction point, I mean where basically you've got an exposed dielectric to exposed conductor exposed to the plasma environment will be the preferential arcing point. And of course, solar arrays is a big one. They are the power source for the spacecraft. They have their own kind of particular interaction with the plasma environment. They degrade over time with aging. Due to their power source, they can have secondary arcing, which is a behavior that we'll talk about later. And so all of these effects are they've been known for a long time, right? And so what's good is that our understanding of this behavior has matured over the years, and we've implemented mitigation. And so through that, we've seen, a decrease in the catastrophic failures historically that's happened through time of these spacecraft. But as time goes on, space programs change, technology changes, and that kind of always sort of requires the necessity for some ground-based testing to simulate the space environment and do specific investigations of behavior that we see. And so one instance of that is sort of the implementation of plasma thrusters. And so plasma thrust technology allows us to kind of reduce the weight of chemical propulsion, increase our payload weight. But it comes at a trade-off where now these spacecraft will spend much longer times in the transit region. And so since the propulsion is low, but over a long period of time, now these spacecraft are spending significant amounts of time in the rather harsh transit environments. And so that brings, special considerations when it comes to charging and aging of the materials. And not only that, these plasma thrusters produce a plasma plume of their own. And so that's sort of a unique contribution, this artificial plasma that's contributing to the natural plasma environment that can enhance certain charging behaviors and effects. And so understanding this, is kind of the first step. One is characterizing, sort of these contributions from the environment, whether they're natural or artificial. And so, these right bar plots kind of give you an idea, at least in the transit region and up to geo, sort of what each contribution, the threat of each contribution can be kind of as a function of altitude. And so, you've got trapped protons, which usually aren't a big concern unless you're kind of in the lower altitudes. And then as you go up, you've got trapped electrons that are kind of always the major concern due to their much higher flux. Atomic oxygen is only concerned in super low orbit, but then this plasma plume that's a result of the plasma thruster, if you're implementing that, is just sort of always there. It's localized to the spacecraft. And um, so we now characterize the environment, and we want to be able to recreate that in the lab, right? And so how do we do that? Essentially, it's just, a vacuum chamber with these radiation sources and specialized measurement instrumentation. And we will cater those sources to the specific environment or a specific scenario that the instrument is going to be in. And we then induce the charging that we expect to see in that environment with these radiation sources. And then we measure any ESD events downstream. And so this is just examples of the instrumentation we have in our Siri lab. We have a 30 keV electron gun, 100 keV electron gun, 100 keV proton gun. And those are sort of like the main workhorses of the simulation. And beyond that, we've got our plasma generator. Now that generator is mainly intended to simulate, thermal plasmas where it's really low energy but really high density, indicative of LEO. And then we've got our detection, which could be anything like the surface voltage probe, a Langmuir probe to characterize the plasma, and any arc detection antennas we've got in there. For sample manipulation, we have our XY stage, which we usually mount our Faraday cup to, which is necessary to measure the incoming flux of the electrons or protons and make sure we're getting the appropriate flux there. We also have a cryocooler that would allow for any sample cooling to also more accurately represent the space environment. Just reiterating on the radiation sources, our low energy plasma system, we can cater the densities to mostly mimic LEO. We can heighten that quite a bit to represent the thruster contribution as well. And we can reduce it quite low to simulate other regions. And so that, along with our high energy electron sources, which can range, we can control the flux of those clear down to picoamp per square centimeter, up to 10 nanoamps, which 10 nanoamps is nowhere near anything to simulate a space environment, but we can use it for aging capabilities of thin films. And of course, our 100 keV proton source, which usually isn't a huge primary concern since the fluxes are so much lower for electron, but if you are in that transit region, it can be of concern in conjunction with the electrons. And so that's a capability we have to implement both dual exposure of protons and electrons here in our lab. And so, so we've got our space environments, and we have these specific charging sort of regimes that exist. So I'm going to talk about inverted potential gradient and normal potential gradient charging. That terminology has kind of been reserved for solar array testing, but it can just kind of be generally used for sort of how the specific sample or instrument is charging up. And so inverted potential gradient refers to when the nearby conductor or substrate is charged to a more negative potential relative to that of a nearby dielectric. And so this is kind of the typical charging scenario that's seen. So this is seen in GEO when spacecraft are coming out of eclipse. If you're in Leo, alone, you're equatorial, you don't really charge very much. But if you start, if your orbit inclines into the auroral region, you can get some negative charging there. And so in this case, the conductor is basically the chassis, where you get high negative charging of the chassis. And then for whatever reason, you have nearby dielectrics that will sort of get charged less negative than that chassis. And so this happens when you're coming out of eclipse. Say you are in shadow, your whole chassis and maybe even nearby dielectrics are charged negative. But then you come into sunlight, and now the exposed face is exposed to sunlight that starts photo emission, and then the exposed dielectrics become less negative than the chassis or nearby conductors. And then if that differential potential gets large enough, you can start to see arcing behavior. And so it's a typical scenario that's seen, and that's recreated in the lab, sort of with the schematics shown on the left, where say you've got a given sample, whatever that might be. It could be, the RF antenna. It could just be some specific material or stack up that you're testing, like the MLI insulation. But what you're doing is you're artificially biasing that sample with a negative power supply, and then you're putting that sample in the presence of some sort of plasma to neutralize the top surface of it. And so in this schematic, I've got the low energy plasma system or use of a 2 keV electron beam. And so if I'm using solar arrays as an example, these solar cell substrates, in the environment are referenced to the chassis. The chassis could be charged to say minus 5,000 volts or something like that. And then when you come into sunlight, the solar glass is then exposed to the sun. You get photo emission. Then you get less negative charging on the glass, and then you'll get arcing from the solar cells substrates to the cover glass. And so the way that we sort of neutralize that top surface in the lab here is with that low energy plasma system. Now that's kind of simulating the LEO environment with the high density and the low energy, but you can also use some higher energy electron beams to exploit the secondary electron yield to sort of neutralize that top cover glass as well. And so those are kind of two different mechanisms to induce inverted potential gradient. And so kind of depending whether, you are in LEO altitudes going in through auroral regions, we would probably choose low energy plasma to neutralize the surface. If you're in GEO, we can simulate that more accurately with using the electron beam. Sometimes it doesn't matter. Sometimes you're just looking for instigation into the arc, and you're looking at the resulting effects. And so, but if it is of concern, so if you were trying to accurately represent the environment and you wanted to sort of get perhaps like inception voltages when you would see arcing occurring, then we can be more particular with the instigation methods, and we can get things like the arc rates associated with that as well. But and of course, there's always just before and after sample degradation to see how it shapes up to all of this. So I've also got sort of our measurement set up here. And so whatever the sample is, we basically tie a cable to it that's fed through the chamber. And in this case, that's essentially terminated to ground via the power supply. And we are measuring the discharge of the current with a current probe. If you'll notice this 2 nanofarad capacitor here, and so we are sort of in this method, you are kind of dictating the energy of the arcs. And so this 2 nanofarads is an example of the spacecraft capacitance to the plasma. And so 2 nanofarads is sort of a ballpark figure of what most spacecraft capacitance is to plasma. That's sort of dictating the energy of these blow-off discharges into plasma when they do occur. And so So even though we are kind of dictating the energy of these discharges, um, it's done consciously and with the value of this capacitor. And like I said, we still get things like the inception voltage information with this scenario, and things like arc rates, and of course the arc magnitudes that are seen. And so inverted potential gradients, typical sort of charging scenario. One of the other ones is the normal potential gradients. And so previously it was the conductor or the substrate that was charged more negative relative to a dielectric. Now this one is where the dielectric is charged more negative relative to the substrate or nearby conductor. And so this is kind of envisioned as basically sort of just direct dielectric charging from high energy electrons. And so um, how we simulate this is basically now if it was the same sample, whatever that may be, we'd load that into the chamber, the cables attached to the sample, fed out the chamber, and that is now terminated to ground. So now the sample is more or less grounded, and the front dielectric face is now exposed with high energy electrons to sort of directly charge that dielectric. And then we keep doing that until we induce arcing, which typically happens at those triple junction points mentioned before, that are the dielectric to conductor interface. And so what's kind of more important here is sort of the accurate representation of the space environment with our electron irradiation. And so how do we do that? So here's another plot of the sort of transit environments where, as mentioned before, the space environment is this huge range of energies and fluxes. In the lab, you're kind of limited by the amount of sources that you've got. And so you kind of want to employ at least more than one electron source to try to help accurately recreate the charging behavior that's seen in the environment. And so how we represent that is sort of shown with this plot where basically you divide up the space environment into these energy binned regions where here I'm showing the space environment from 1 keV to 20 keV being represented by a 20 keV electron gun, and then the region of the space environment from 20 keV to 100 keV is represented by the 100 keV gun, where the flux of each of those guns is now scaled as the integration of that plot within that region. And so you're not just picking 20 keV and shooting it with that flux, you're shooting it with 20 keV that's representing the flux of that 20 keV and everything below it. Likewise for the 100, it's 100 keV electron gun, but you're representing the fluxes of 20 keV to 100 keV. And so that's how we try to mimic the space environment the best we can. It's with this sort of dual source irradiation that's covering fluxes throughout the entire region of interest. And so while we're doing this, typically, you can run your surface voltage probe to get charging behavior of the sample for given flux periods. And then, of course, likewise, we are just measuring the discharges with our current probe and our oscilloscopes with Faraday cup measuring the in situ flux. And so this isn't as typical of a charging scenario. It's mostly regarded for shadowed regions in highly energetic environments like geo or auroral. But shadowed regions, are the entire backside of the spacecraft, anything that's shadowed by an instrument or any extended object. And so, even though it may not be typical, it's still a reason for a concern and can still happen, especially during eclipse entry and exit. And so, it's something that we try to advertise. We say, hey, you want to look at this charging behavior, let's try to look at both aspects of the inverted and the normal potential gradient, not even necessarily just for the solar arrays, which is where this terminology kind of originated from, but for any other instrumentation that you're planning on using. So I'll move on to sort of the prime example, which is the solar array ESD testing. And so there's a standard out there, ISO 11221, that sort of outlines sort of general guidelines for how to carry this out. But there's plethora of journal articles and much investigation into how to properly carry out this testing. And so what is the ISO 11221? What is a layout? Primarily, it's for investigation into the secondary arc qualification or mitigation of a solar array design. And so if you're not familiar, secondary arcing is basically you've got an array, you've got two parallel strings to each other. Those strings will have a differential voltage between them. But now you're in a harsh environment that's producing primary arcing on the solar array, and you can generate a primary arc in between the gap of those two strings. And so what that primary arc does is it essentially produces a temporary bridge, a conduction bridge between those two strings. And since now those strings are, power sources, they will possibly essentially short between themselves with the power generated from them. And that can produce what's called a secondary arc. And so, or a sustained arc. And so this sustained arc could be fleeting. It could be as long as the primary arc is, or it could last longer, or it could even last indefinitely, depending on the power, the voltage, and the current behind the strings. And so this is something that's of concern when you're going through solar array design is, hey, I want to maximize the footprint of my solar array, and I want to get the most power out of it, say. But there's some limitations to that due to these plasma interactions. And so secondary arcing is the big one. LEO or plasma current leakage is another one. So if you are a high voltage array that's 100 plus volts, and if you're in a high density plasma like in LEO, or if you're implementing plasma thrusters, you could get leakage current from the solar array to plasma that's represented as a power loss in your system. That's outlined in the ISO standard. And another big thing of investigation is the something called the flashover waveform or the flashover events. And so before I called this the primary arc, which is basically arcs that sort of are the instigation arcs for the sustained arcing between cells. But this primary arc essentially is a ESD event that produces its own plasma bubble that expands outward. And if your array is large, what that's effectively doing is sort of, as that plasma bubble goes out, is it neutralizes the charge buildup on all the cover glass across that array. And so typically primary arcs the strength of the primary arcs are dictated just by that capacitance of the spacecraft to plasma, so say nanofarad range. But now what happens is that that primary arc instigates this plasma bubble. It goes out, and that neutralizes the capacitance of the charge that's built up on those cover glasses, and that neutralization forms itself as a neutralization current that goes to that primary arc site, and you can get some pretty large discharges as a result of this flashover. And um, so simply stated, flashover is instigated by a primary arc as well, but it turns into a much larger event due to the neutralization of the capacitance over the entire array. And so if you've got a large array, this can be a pretty large waveform. And so this plot here is showing it going, 800 microseconds long. So a significant event with a lot of energy stored. And this picture on the right is a very good visual representation of sort of how that plasma bubble goes out and is interacting with the other solar cells um, and adding to the flashover waveform. And um, so this testing is a big part of solar array design and is kind of one of the main areas of concern when it comes to ESD events on a spacecraft. And so that's one of the things we focus on. Essentially, what you're doing is some people don't have the luxury to put the entire array into a vacuum chamber to do this test. And so what you do is you take a representative coupon of that, which is just it could be 4 to 6 cells with 2 strings, and that's put in the chamber. And then you put in an equivalent circuit to represent the entire array when you're doing this testing. And so that's mostly related to that flashover I was mentioning before, where you determine what the flashover would be for the actual array, and then you are then simulating that on the coupon, on a representative coupon in a smaller vacuum chamber. And so I don't have the circuit shown here. It's listed in the ISO, but essentially what the circuit is just it's a way to mimic the power of the solar array, the string-to-string differential voltages, and the current provided in the event that there's a primary arc in that gap. And then we start inducing arcs in that gap to see if we get sustained arcing. Excuse me. And so, with this testing, we're able to help solar array designers determine what are the safe string voltages and currents that would and gap distances that would allow for no secondary arcing to take place. And so I won't go too much in detail about this, but just know that the flashover waveform is important as far as characterizing it for this testing. And then we run through basically all the possibilities of the voltages, the differential voltages and currents, and we see what the sort of safe nominal power an array can run at that would prevent secondary arcing. And so here's this plot here is an example of some characteristic waveforms of this testing. The purple line, the only ones you really need to focus on is the purple line, which is the flashover waveform. And you can look at this blue line and you can see it's sustained at 3 amps for the duration of the flashover, and then it ceased. And so this is an example of the flashover provided that bridge between the 2 cells, and there is sustain from the cells occurring, but it only lasts for the duration of the flashover waveform. And so that's typically a good sign. And so if you were running this test and you were seeing a flashover waveform, and then you were seeing that sustain going beyond the duration of that flashover, now you are having sort of a true sustain that's beyond the flashover. There's no more available plasma from the flashover that's contributing to that bridge. It's simply the power of the strings themselves that are sustaining the arc. And these arcs can be catastrophic. They can be permanent. And so that's why it's such a large concern for people, because we've lost, satellites because of this. And so it's not only that, there's differences in solar cell design and solar array design that kind of usually always necessitates the need for this type of testing. And so, I'll also discuss material aging. And so for the spacecraft charging, we're always concerned with, how charge is being deposited, how things are differentially charging. We're measuring the arcing behavior, but we've got these missions that last, 10 to 15 years, or now you're going through the transit environment through an extended period of time, and you're seeing aging effects. And so aging effects is something that's always also been of concern because that changes the material properties of the materials that are being bombarded, and it can change the charging and arcing behavior. And so one thing that we can do personally, even just with our 100 keV source, is try to age thin films. And so what you typically want to try to do is accurately represent the aging that will be seen for a given environment. So say you're 15 years geo, you want to get a dose depth curve for that environment, for that amount of time, for a given material. And this top right plot is kind of that the black line is a representation of that, where that is sort of the dose as a function of depth that the material is seeing. And so you want to try to accurately represent that with your aging, so that you're kind of, mimicking the actual aging that's occurring. You can do that with our monoenergetic sources, and with the help of our simulation, we're able to determine, one, the dose depth profile as a result of the 15-year geo, but also the dose depth profile provided by the monoenergetic source. And so the larger plot, there's these multicolored lines that are showing the different contributions from different energy sources, and the superposition of those would just be the total dose, or the total dose depth profile that is seen. And so on the top right, that's what that red line is. That's basically a superposition of different aging steps from a monoenergetic source. You can see it starts falling short about 60 microns, because it is just a 100 keV source. And so this is kind of more or less only applicable to thin films, but there's lots of thin film applications used, space applications. And so this is sort of our approach when it comes to material aging. If you do need deep aging, you can just send it off to a cobalt-60 source, where you're sort of getting a flat dose depth profile that you choose a nominal value at. But you do get certain different effects from X-ray deposition or energy deposition versus proton or electron deposition. And so this is just a methodology we've tried. And I'll also highlight that, the use of the simulation software to produce results like this is pretty key. And Um, there's glaring differences between what software simulation can do and what in lab testing can do. And so what we've, but understanding that and being able to use them together is sort of a big part of our approach to our in-lab testing. And so we will rely a lot on software simulation to help guide and dictate how we physically test something in the lab. And so we know that there's pitfalls with how you represent the space environment with the lab, but with use of the software, we can understand that and try to mimic it the best that we can. I'll just add some other notes of what some of our other capabilities are going off of aging. We do have a UV aging capability, not of the largest concern compared to the ESD, but it can be. And so if you are in geo for 15 years, you do have the typical, deep aging from the electrons that I mentioned earlier, but you could have an influence from the UV. And so we do have an acceleration factor of about 270 with this UV source. And so we're able to sort of UV age whatever it is you need relatively quickly. That could be thin films, optical thin films. It could be cover glass. It could be coatings. And so also how we usually check for degradation is, our benchtop spectroscopy. And so if it is an optical layer, we can see how that changes with both UV and electron aging. And a lot of this is kind of touched on sort of these material properties. And so I have a colleague giving a talk, I believe on Friday, about the importance of material properties and our understanding of them when it comes to determining the charging behavior. And we do have a secondary electron yield chamber that is able to measure the yield of conductors and insulators. And this is sort of directly how material charges due to electron bombardment. We're almost finished with our constant voltage conductivity chamber, which is just a way to measure the conductivity of the material. Also directly related to sort of the charge migration and the current balance when you're determining overall charging. And so those are other capabilities that we have that I'll leave Justin Christensen to talk about on Friday. And I'll just leave it here for now and see if you guys have any questions. Thank you.
Thank you, Brian. We can go ahead and transition into the Q&A portion of your presentation. Looking at the queue, there aren't any questions currently submitted, so I have a few that I could ask you to hopefully start some more conversations. So my first question for you, Brian, is where do you see the greatest need for future research in spacecraft environment and interactions? Are there particular materials or phenomena that are poorly understood that that you think are worth researching that maybe we've touched on here?
Yeah, so I mean, I guess the plasma thruster is kind of an example of that. Also, we are pushing to go to the moon, and so the Gateway program is basically the joint international effort to create basically the International Space Station, but around the moon. And so that's going to serve as a depot for future missions there. And so other considerations now that you're talking about the moon is all the dust that's on the moon. And so you get triboelectric charging from that. And so moon dust is extremely fine. And just from walking around on it, you will charge up. And so there's a lot of interest with the sort of manned excursion and the spacesuit considerations going into the charging effects. And so, um, since there is, human life involved, there's, zero room for error there. And so, a lot of investigation is going into modifying spacesuit technology to handle these ESD events, not only as a result from this charged particle environment, but also from tribocharging from walking on the moon. And so that's another example of how us branching out in our space program is kind of necessitating different avenues of investigation of ESD phenomenon that are critical, since it is now a human life that you're talking about.
That's interesting. Yeah, thank you for that. We do have a few questions submitted to the Q&A queue. First one being, what are the charging characteristics for natural versus thruster environments?
I'm sorry, say that one more time.
What are the charging characteristics for natural versus thruster environments?
Oh, okay. So, so basically with the thruster, you're adding, much higher localized density uh, to like around the spacecraft. And so, and you're adding higher energy portions to that plasma density. And so, essentially, if you're talking about direct charging of the chassis, you're just essentially enhancing that. It's not a lot if you're talking about direct charging. And so, but it could be, and it only really takes, 100 volts, 200 volts to instigate arcing behavior. And I say 100 volts, 200 volts differential charging between, two objects at like a triple junction point, like I mentioned. So there is that. And then there is, of course, this leakage current I was talking from the solar arrays. And so you've got a solar array, it's producing power, it's at some biased voltage. But now you're basically in the presence of a highly dense environment, and you're essentially just leaking some of that current out into the plasma environment. And so that's really only a concern that previously that was only a concern for LEO environments. But now, if you've got a plasma thruster, and even if you're in geo, you could still be maintaining a pretty high density near the vicinity of the array that could be producing this leakage current. And so there's sort of there's sort of a geometry factor there. People are trying to figure out how to point these things away from the array, but because like with this contour, obviously the plasma is heightened downstream to it, but it's there's just there's a lot to think about there. And so those are basically the biggest areas. Is one, it can sort of enhance the charging itself of the chassis, and two, you run into these current leakage situations with the solar array or any other degradation of any sense. It could be optical degradation. So basically you could be ablating nearby surfaces with this plasma from the plasma thruster, since the ion energies coming out of this thing are 20 to 40 eV or something. That's more than enough to start ablating nearby surfaces.
Thank you. We have another question here. A few now have populated in the queue. First one, are you using specialized data acquisition systems to collect the raw data from your sensor groups?
Um, the only specialized stuff we've used is for our video camera. And so when we're taking images like this, um, that's an in-house software that we've made that's plucking frames from the video that we're taking. And so it is technically taking video, but what we're recording are images of the arc. And so that's specialized software where it's looking for a intensity change in the frame. And if it sees an intensity change, it's plucking images from a buffer of the frame during the intensity change and before and after. But as far as anything, all the ARC collection, that's basically just using current and voltage probes into an oscilloscope. There are other specialized things with the secondary arc testing. We have a circuit interrupter with that system, and so it's detecting when a sustained arc is occurring, and it will actually shut down the power so that we don't burn out the coupon. But as far as measurement, it's all pretty straightforward when it comes to the arc detection, except for maybe that video software.
Okay, great. Next question is, in the case of launch vehicles where the flight time is limited to a maximum of 10 minutes and the peak altitude reaches up to 580 kilometers, is it necessary to perform specific analyses such as plasma-induced ESD risk simulations? What critical points or recommended precautions should be taken into account to ensure system reliability under these mission conditions?
As far as I know, that's something I've never taken particular attention to. But as far as I know, there's no. I mean, you could call that Leo conditions, where that's just kind of the thermal plasma. I don't know what kind of charging you get from sort of the tribo effect, meaning as as the launch vehicle's traveling, it could be charging just from the kinetic uh, friction between the chassis and the air or the plasma. I don't think that's a really big concern, especially because it's all one encapsulated shell at that point. And so I imagine that there probably could be some events, and that's something we don't really investigate. That's an interesting question, though. So um, my inkling is to say that I don't think there's like a huge threat there because the launch vehicle hasn't separated yet, and it's still basically just the outer shell that could produce any charging, but that would be pretty uniform over the entire um, shield or outside of it. And so I don't think you'd expect any differential charging in that sense. And so it's only when you get the spacecraft deployed where you've got all these exposed interfaces and different materials and um, situations like that that can produce arcing. That's an interesting question, though.
Yeah, certainly. Okay, next question is sort of a two or three part question. So I'll start here with just asking, how do you consider incident electron energy relative to potential charging voltages? In particular for LEO, it is up to 100 keV too conservative since it allows for charging up to 100 kV? Is 20 to 30 keV more representative, or how do we think about a representative monoenergetic electron source for spacecraft charging testing?
Um, let's see, can you try to break that up again?
Yes. So the I think the main point of it is, how do you consider electron energies relative to potential charging voltages? For LEO, is 100 keV too conservative?
Right. So I guess I'll say is that for Leo, if you're equatorial Leo, you're not charging really at all. It's basically you're charging to the plasma potential. And so it's really if you're just so environment specific, and that's why it's important to create a plot like this where you want to know what the sort of worst case flux and energy that you're going to be receiving. And so with these differential flux plots, you see what energies and fluxes you are going to be seeing in the space environment. And so then the question is, how am I supposed to be able to represent this in the lab with my monoenergetic sources? And so that's sort of how I was trying to explain here, where you are using just two monoenergetic sources to represent the space environment up to 100 keV, but you're doing it with fluxes that is representative of that entire region. So I don't know. I hope that answers that question.
I think there's also another part to the question that might qualify it a little bit more, and that is, do you also vary the fluence or flux with respect to energy levels to make them more representative of what is in the actual environment?
Right. And so that's essentially what these shaded regions are. And so um, it's ooh, these plots are um, they're kind of difficult to understand, but basically um, the red shaded region is an integration under that curve, and that gives me the flux to the total flux within that region that is then simulated with the 20 keV gun. And so the 20 keV isn't just representing the flux in the 20 keV line, it's representing everything in that shaded region. And so that's where the lab simulation is, a gross approximation really, because ideally you'd want an infinite number of monoenergetic sources, each at that energy's flux, but we can't really do that. And so we integrate under the curve to represent the flux from 1 keV to 20 keV, but using just a 20 keV beam.
Okay, great. Next question is there a way to simulate the charging effects on solar arrays in a way that we can take a specific solar cell design and analyze how different the arc characteristics can be, or is this purely understood through verification?
Yes. So essentially, the arcing behavior is dictated by the solar cell type, the manufacturing. So the cover glass overhang, is it grouted? Is it not grouted? And so it's all very specific to those parameters. And so um, that is sort of the whole point of the ISO testing, is to take a representative coupon of what you're going to fly in both cell type, uh, gap distance, cover glass construction. Is it grouted? Is it not? And then run our testing to see sort of what the nominal arcing behavior is for given power parameters. We can also discover the inception voltages, so at what differential charging potentials produce those primary arcs. And so that's all characterization we can do. And yeah, it's very coupon specific. And um, so yeah, if we were going to do testing for someone who uh, wanted to look at all these differences, they could give us a slew of different types of coupons, and then we can investigate all the arcing behavior for a given environment.
Okay. Next question, are there active investigations into making electron guns that are not monoenergetic, having more realistic spectra?
There are ways. So foiling is a method. So essentially, you start with a monoenergetic source, and then you put a foil in front of the beam so that as the electrons pass through the foil, uh, it alters their energy spectra and their flux. And so yeah, there are methods like that. There are also methods where you could try modulating um, the gun energy. And so it's a monoenergetic source, but I guess I should say it's monoenergetic, but we control the energy. And so that's something we haven't toyed with a lot where say if I was trying to represent this red region here, right now we're just doing it with 20 keV energy of the beam, but we could be modulating that energy. You can't do it very quick, but what we could do is be changing the energy of that beam from 1 to 20 keV, over a relatively short time scale within like a couple of minutes or something. And so that's something that I think would work. Again, it's not super indicative. And I think that if you maintain the 20 keV, that could be representing the worst case, because you're kind of generating sort of the charge density level at sort of that higher energy. And so, so yeah, there are methods with the foiling or the modulation. And that's a good question. And I'm not sure, really what the exact effects of that are. But so yeah, it's difficult, but it can be done.
Okay, and we'll try and wrap this up with one last question before we go to the next presenter. So, last question here: is there any merit to irradiating with both protons and electrons simultaneously to simulate the plasma environment? Is Siri capable of doing both at the same time?
Yes. So to answer your question, yes, we can simulate them at the same time. And so our proton gun, which is it the way it functions is it basically ionizes, incoming neutral gas, and that's accelerated downstream. But the aperture, um, the construction of this is made so that the pressure inside the main test chamber is still much lower than the pressure in that ionization chamber of the proton gun. And so we are able to simultaneously irradiate with protons and electrons. And that can be of importance. Normally, if you're just talking about GEO, the flux of protons to electrons, or the flux of electrons to protons is much, much higher. But if you looked at this bar here, if you're slowly going through transit, you could have a somewhat equal contribution or even a higher contribution of protons to electrons. And so the interplay of the charging between those two is interesting behavior that may need to be considered and may even need to be considered in higher and higher altitudes. And so it would be interesting to investigate that.
Okay, great. Thank you, Brian. With that,
Awesome,
it's
thank you.
now time to conclude the first presentation of this session. So as a reminder, any questions that will be asked that were not answered today will be addressed via email specific to Brian's presentation. We'll now turn our attention to our second speaker. As I introduce him, he will share his screen and open his presentation. So our second speaker today is Michael Campola. Mike is currently the leader of the Radiation Effects and Analysis Group at NASA's Goddard Space Flight Center. Michael joined the Flight Data Systems and Radiation Effects branch at NASA in 2007. Throughout his career, he has been working on the center's spaceflight projects to capture system-level radiation responses through analysis and ground-based testing of semiconductors, with research into promising future technologies through the NASA Electronics Parts and Packaging, or NEP program. The primary goal of this work and research is to provide support for mission success through the implementation of hardness assurance (RHA) practices. He's a member of the Institute for Electrical and Electronics Engineers, or IEEE, and the Nuclear and Plasma Sciences Society, NPSS. Without further delay, I give you Mike.
Thank you so much, Matt. And hello to everyone that's out there. Just a spot check that you can hear me okay?
Audio's coming through great.
All right, wonderful. So I want to thank, first of all, EMA for having me again. We had an in-person workshop last year and have the benefit and the privilege to talk to you all today again about similar subjects. So let me go ahead and get this working. Let's see. All right. It's not advancing. Let me try again here. Pardon that for a second. Wow. Thought I had it already. Okay. All right, let's see now if I can get things going. All right, here we go. So the topics that I wanted to address today, and this is an intent to bring us all onto the same page, to talk about the effects that radiation can have on our spacecraft systems, spaceflight systems, and the electronics inside. So I'm going to do a real quick push through environments for spacecraft so that we're all on the same page, and then I'll talk about the different types of radiation effects and how they scale with complexity. We'll go through some radiation hardness assurance fundamentals and talk about some test considerations. I'll watch the clock. If we have time, I'll talk a little bit in detail about anomaly resolution. And so I'll get going through all of the stuff that we have to go through today. So the natural space radiation environment, I'm sure a lot of you are aware, is a very dynamic system. So we have solar maximums and minimums, which really dictate the number of solar flares that you will see per unit time. Same thing as coronal mass ejections. So there's no cycle of the sun where you won't see those things happening. It's just that the amount of them happening per unit time can be realized in more active and less active states. Closer to Earth, we deal with the radiation belts, which were mentioned and you heard Brian talk about earlier. And we also deal with geomagnetic storms and a background that we are awash in of galactic cosmic rays, very high energy particles. Naturally, there are a lot of threats to the system. It is a very harsh environment that we are up against. My focus and discipline is on the particle radiation, which can result in charging, ionizing and non-ionizing dose, single event effects, and even surface erosion. For the sake of clarity in what I focus on with electronics, I'm going to be talking about the ionizing, non-ionizing dose, and single event effects today, but that doesn't mean that any of these are less important to worry about. I think of the sources for the radiation effects that are realized in electronics, and we can bin them into different groupings here. So we've got galactic cosmic rays, which are very energetic supernovae remnants. They originate outside of our solar system. We have the solar activity, the sun, which is a major modulator of the environment that we are up against. And any planet with a magnetic field is going to have some radiation belt or trapping of charged particles. Here you can see the protons on the left and the electrons on the right, just meant to show you them side by side. The magnetic field strength, of course, determines the energy and distance away from Earth that those particles are trapped in. We can look at those again in this pictogram of where satellites end up usually, and we talk about the inner belt and outer belt, and where satellites are going can really be an important decision or driver of what your radiation environment is going to be. Predominantly, protons are a primary concern for single event effects, and electrons contribute to dose and charging effects. You heard Brian talk about those earlier. But we have all of this kinetic energy and all of those different sources. And so really we can look at them all together. Here I'm just showing an example of one heavy ion nuclei. This is oxygen nuclei. They exist in the solar wind, they exist in CMEs, they exist in solar flares and galactic cosmic rays. As you go up in energy, there's the potential for risk of interaction with the electronics that you have inside, mostly because they're going to make it through your spacecraft shielding. That's usually the first thing that people jump to whenever you're asking about radiation is, well, can't I just shield that radiation out? Well, we do have ways of modeling that shielding, and some of the most simplistic ways is to just assume spheres of a single material, such as aluminum. This is basically what we do for any first cut of the dose that you're going to have to deal with inside of the spacecraft where the electronics will live. But we can go to higher fidelity modeling platforms and do full-up CAD models and understand pinpoint locations, doses that we are going to see. It's somewhat more informative to talk about what is happening to the energy spectra that you are transporting through a material, whether it's complex or simple. I've tried to line up the y-axis of all of the contributions in one orbit before and after 100 mils of aluminum. What you can see is that you've knocked down that low energy component, those things that are in the KeV and the low MeV can be attenuated. And so this is where spacecraft charging on the skin wasn't shielded out, but you did shield out the lower energy, large amounts of particles that were lower energy. Once you've transported that through, it's hard still to describe. As you can see, there are curves here for helium, hydrogen, carbon, on and on through the entire periodic table. But what we need to do is to be able to describe that entire environment. And so what we end up using is a metric called LET. On the right, you can see that it is very high energy particles that create low LET, and it is lower energy particles that can create high LET. If you've not heard of this metric before, it's analogous to stopping power in material. And so what it really is talking about is energy deposition. It's normalized to the material that is in question. In most of our cases for electronics, we use silicon to describe the energy that's deposited or the charge that's generated inside. A way to visualize this is to look at its interaction with materials, and a low LET may sputter or interact with the material sparingly, whereas if you go up in LET, you start seeing more of a charge column that's created, or damage column that is occurring in the material that you're interested in. So that LET metric is really useful for us because we can describe all of those energies of all of those different species of ions in this LET metric and represent the environment in one curve. So here I'm showing, two example environments at two different times in the solar cycle. So the lower curves on the left would be a mission that was going to the International Space Station, whereas the curves on top would be something interplanetary. And so you can see where you go matters. You are changing orders of magnitude in terms of the flux that you are experiencing of these particles that result in LETs of different values. These are reverse integral plots, so any point that you pick is that flux of particles at that LET or greater. Can be somewhat counterintuitive, but you can see they have this characteristic shape with a steep drop off later on in that spectra. That is known as the iron knee, and that is where things become more and more rare because of the competing effects during supernova explosions. There's so much in all of this, but I'll be happy to answer more questions about the environment if you need it. the left versus the right is talking about normal background conditions versus peak conditions whenever a solar particle event occurs and it's coming your way. You can just pay attention that the y-ordinate on the left is a scale per day, and on the right it's a scale per second. I try to work to explain this to folks of the problem set that they're up against. And I'll just put this succinctly. If we were talking about an LET of 10, if you were to spend a full year at the background of ISS, you may have a bad year in the case of A, where something that was sensitive within your design got hit, or you could have a good year where it was not hit. But if you were to experience a flare, you have copious amounts of particle strikes, and it is more likely that your sensitive region would have gotten hit. If we compare this to a different orbit now, if you were to think about lunar background where a lot of missions are going, you now experience the same thing that you experienced in a year at ISS in one day. And so just trying to put into perspective the radiation problem set that you're up against. I also think it helps to look at this. So when a CME or flare is coming in your direction, you can have noise on your detectors. Here you can see those coronal mass ejections causing that snow, and eventually you will see whenever it shows up on that detector. So now you have to ask yourself the question of whether or not your system was able to function the way that you needed it during that, that particle flux and that hugely dynamic change of what you were dealing with. We can look at a solid state recorder that's counting single event upsets. These are bit flips in memory. And we could see a nice steady background that is driven by the trapped protons and galactic cosmic rays. But we can also see the solar flare conditions causing peaks in the error count. And really you just need to know, without information on how the flight design is using the data that's in that memory, we don't know if we're in and out of bounds, or if we're going to be okay, or if we need to add mitigation to our design. So that's a lot of what we are trying to figure out, is the practical outcome in the system of these high energy particles and what they're causing inside of the electronics at a device physics level. So ionizing radiation, it can be described into different categories as well. Total ionizing dose, total non-ionizing dose are cumulative damage that occurs, and single event effects are what they sound like. They are the effects that happen from one single particle. They can be either non-destructive or destructive, and so they present a unique risk to spacecraft and spaceflight systems. The takeaway here is that those TID and TNID effects happen over the mission life, and SEE can happen from one particle and can be instantaneous, much like the electrostatic discharge that that Brian was talking about earlier. If you have charge buildup before it bleeds off, you can have the arcing that he was seeking to characterize, and CRE has that capability of testing for that. So I like to look at this as a twofold problem. If I put this in terms of a bathtub curve, right, a probability of failure over time, that typical bathtub curve, dose effects, those cumulative effects, look like early wear out in the nomenclature of the reliability. But single event effects look like random events in time. And so the probability of failure for something that you allow in your design is the same on the first day as it is on the 1000th day. Now, there's some nuance, of course. There are more chances for that failure to occur if you're getting hit by a solar flare a lot of times. But for all intents and purposes, it's raising the bottom of the bathtub curve if you are allowing single event effects to be part of your design, which is very hard to get away from these days. TNID, this is just a pictorial way of looking at particles with energy coming in. The higher energy that they can cause larger and larger clusters of damage. You start with point defects, and eventually you get into these tree-like structures in the silicon of damaged clusters. And here's a more detailed modeling outcome of what one of those clusters would look like. Well, if you're looking at devices and how this might impact you, here's an optocoupler that was no longer able to turn off because of the damage and leakage that occurred after being subjected to a bunch of protons. Here's discoloration of colored cover glasses in front of a camera, showing you the image of the Earth turning more and more orange over time, eventually darkening. And here's a detector silicon itself that was tested on the ground, and you can see damage sites that occurred within the detector itself from a particle actually depositing a lot of energy in one location. For TID, it's the creation of charge. Electron hole pairs get created, there's charge migration and eventual trapping. When that charge is trapped in key locations within a semiconductor device, it can lead to things like functional failures of complex circuits or very parametric failures of basic device properties like MOSFET threshold voltages. So you may have been able to turn off your MOSFET before, but the voltage doesn't do its same job. And so we see failures from TID as well in devices. But overall, the trends in commercial devices, right, is that feature sizes are shrinking. And so the isolation and oxides have been shrinking. And so there's less and less volume for charge to get trapped in. So we see better performance with those cumulative effects as the feature size shrinks. We see the converse happening whenever it comes to the single particle effects. As the feature size shrinks, you start to see more and more impact from lighter and lighter ions. And so sensitivity to single particle effects goes up while parametric failures and stuff get pushed out to the right. And our missions tend to get shorter. And so we're winning in terms of the cumulative, we're losing in terms of the instantaneous. So we spend a lot of time focused on those high energy effects. And the instantaneous, in a simplistic way, if you were to look at a diode, ion comes in, creates that charge column or track. It disturbs the contours of the depletion region in between the two different types of semiconductor material. And that has ramifications on what the device is going to do with the charge based on the potentials that the user has set across it. We have a myriad of namings and acronyms for the effects that happen in different types of devices and different device technologies. It's helpful to look at them in terms of destructive and non-destructive in different categories. So on the right is a really great pictogram of the consequences on the x-axis versus the persistence on the y. And so the destructive SEE can be permanent and catastrophic, whereas things like transients can be local and temporary and might just be a nuisance within your design. It's a very useful chart from Ray Ladbury. I tend to put it in all of the talks, but I wanted to show you electrically some of the destructive effects, what's going on. You will see shoot-ups in your current, and you may or may not have a system that's able to deal with that. And sometimes testing and verification and mitigation can be more costly than just replacing the part. And so we spend a lot of focus and time looking at these different types of effects and what we can do and whether or not they're flight worthy. A way to look at those damage events in pictures is to understand that we use those naming conventions for the physics of failure that's going on. So a latch up is talking about a parasitic structure in a device that gets turned on, typically in by CMOS or CMOS devices. It's a thermal runaway, so you end up pulling so much current that the device can either burn itself or the bond wires. It can melt metallization in the device connections that are occurring on the top of your active layers. And so that's a very bad day if you have to deal with that. Same thing with single event burnout, gate rupture, and dielectric rupture. They seek to define the physics of failure. And this is where you have an electrostatic potential across something like a gate or even a holding voltage across the drain of the device. And where the device gets struck, basically the potential energy overtakes the dam. You're basically knocking a hole into the dam and the whole thing cascades, and then you have a fail to short or fail to open that can occur. And these are what some of those damaged sites look like inside of different things like a diode or a DC to DC converter. Again, a bad day, irreversible damage. But it's not all bad, because some of the impacts are non-destructive. These can just be a nuisance and things can go on as planned, but sometimes they can accrue and result in things like multiple bit upsets that might break your error detection and correction. These are nuisances, but they have to be planned for in a design. And so there's a lot of work that goes into component selection and application verification. Some of the more sticky things are single event functional interrupts. We've gotten to a place where our devices like SoCs, FPGAs, processors all have so many different types of structures and so many different sensitivities that the single event effect can just disrupt all of that timing and operation. You can get Cepheids here. I'm showing like what was supposed to be a transmitted image through an RF transceiver. You can get things like stripes. You can get things like snow. You can almost make out the image of peppers in the background here. But if this was your science data, you'd be having a bad day, even though all it takes is a power cycle to refresh it. But if you miss the shot of the once in a lifetime event, then you've failed at the mission level. And so it's key to understand and plan for these things. In summary, here are some of the risks to electronic parts. I'll just note that combined effects also need to be considered. Typical mitigations at the system level are to shield for those cumulative effects, because if you're knocking down the particles that are most present at the lower energies, you are dramatically improving what happens for dose. You can't get away from it altogether, but it does go a long way. A little bit of shielding goes a long way. And we like to avoid allowing destructive single event effects baked into the design without a really proven and tested mitigation scheme. And we anticipate non-destructive effects. Knowing what SE signatures we're up against is really key. We end up filtering power supplies, using EDAC, using watchdog timers, and power limiting susceptible devices that might have inrush currents that we don't want to deal with. But being able to power cycle a part, board, or box where you don't know the answer can also go a long way in terms of system health and mitigation. Not a catch-all, but it's there. Radiation hardness assurance overall is everything that we do to try to make these designs work. And so we define the environment using environment models that are up to date with satellite data. We determine project requirements and specifications up front so that we know when we are up against the limits. We can evaluate that design to those requirements, and eventually in flight we do an evaluation. So there's a lot of cross-pollination with other disciplines that happens, and there's a lot of good work that happens up front. Timing is everything. If you are all the way to where you're at INT, there is not much that a radiation test or radiation analysis is going to do for you other than help you determine root cause whenever the failure is realized. And so, especially when you're using new technologies, you want to be involved in the formulation of the mission design and have your inputs heard. It's very difficult to assure complex devices, and I know this is an eye chart, we're not going to read it all, but what happens is handshakes between someone who is focused on technology feasibility. This is research in the field of what could be promising for radiation responses from devices. Demonstration of architectures that are candidate for spaceflight. And then finally, system assurance whenever you actually know what environment you're up against and you actually know what the end user needs to get out of that part. And it's all of these efforts going on in concert that actually allow us to assure something that's complex. It's not just one radiation test that clears the device for uses in all cases. And that's more and more true as we go on. If you are trying to mitigate with system architecture, meaning you know your part has susceptibilities and you want to integrate it into the design and you want to make sure your mitigation's going to do a great job, you need to understand what the severity could be for a given mission. And you need to understand whenever you see that application signature, if it's going to allow your system to continue to function, if it's going to interrupt it, or if it could be catastrophic for what you're trying to achieve. If it's catastrophic, you need to add additional mitigation. If that's not useful or cost effective, it may be that you need to remove that susceptible component from within your design. Everything in between is something that you need to carry, anticipate, document, and understand whenever you see it on orbit, what recourse is necessary, if any, or if you can just ignore it. But that needs to be captured somewhere so that the teams that are working on it after you understand what they are up against. I could go through an example system or function, so I've really dumbed it down here. Just 3 devices, a power management IC, a system on a chip, and memory that's storing the boot up code. These are made of different device technologies by CMOS and CMOS in this case. The flash memory has floating gates as well. And I'm thinking of different operational states during the mission. I might be in a safe state where before I ever get turned on. I need to load the boot image in order to do my operations, and these different operational states mean that the devices are doing different application jobs at different times. There could be error accumulation during the safe state, there could be interruptions that occur when it's trying to load the boot image, or there could be corrupt data during operations. All of these examples are just something to deal with. In the safe state, you might be dependent on the power management IC and what's in the flash memory, whereas during the operation of loading a boot image, which might be very short in a matter of time, depends on all 3 of these chips doing their job robustly. And during operations, maybe what's in the flash memory is no longer of consequence and you might be okay. You can rack and stack all of the error rates that you might see, and you might be able to understand where you need to focus your resources, whether or not you're determining if mitigation needs to be implemented or if a part change might need to occur. If you stack all of the things that are possible that you've seen either from generic data on the devices or testing that you've done yourself, you can help yourself get to an iterative solution of what the next step could be to make a more robust system. And that allows you to communicate with your stakeholders. And those stakeholders might not be who you always expect. Sometimes you need to rely on board designers, system engineers, or even operators who might not have been selected at the time when you're doing formulation for what the electronics in a design are going to look like. So you have to keep that in mind, that these stakeholders change over time as well. Testing for radiation is not the same as actual conditions, but what we do is try to put together a ground test that best represents the thing that we are trying to observe and characterize. Sometimes it takes multiple tests to actually get to the answer of what you need to do from an engineering judgment call. And so this is very front of mind for anyone who's in radiation effects. The key elements, if I'm trying to sum it up, is that as you go to higher and higher fidelity, there's an increasing cost. And as you move away from thorough testing, you are going to have to accept more risk. For total ionizing dose, we typically use energetic photons. For total non-ionizing dose, we use monoenergetic protons or neutrons. And for SEE, we typically use heavy ions, protons sometimes, and secondaries of neutrons or pulsed laser if we can, just to try to make it cheaper. For the energetic photons, there's a sweet spot of energy where you're doing a lot of electron hole pair creation and you're getting nice coverage over your entire die. For total non-ionizing dose in those monoenergetic sources, there's a sweet spot of energy where you are causing a lot of the Coulombic interaction, more Coulombic interaction, and causing more primary knock-on atoms. And we're able to describe the entire environment's damage in the same amount of damage that would be caused by the monoenergetic beam that we are testing with. And that is called non-ionizing energy loss. The equation is shown down here. For the cumulative damage, we can predict when failures are going to occur by doing statistical modeling of the environment that can be achieved behind different amounts of shielding. And if we have a statistical representation of damage of devices, like where devices failed at, down here on the bottom, we can put those two together to understand the failure probability for different aluminum shielding thickness for different orbits that we are going to go to. And this works relatively well for things that we've seen on orbit and preventing failures that way. For SEE testing, where we use heavy ions, there are a lot of different facilities worldwide, even some that aren't listed here. But these are very high energy per AMU facilities that give you good coverage over the die. In this case, it's kind of questionable whether or not I'm hitting all of the structures in this SRAM. But for all intents and purposes, you are describing that LET, that charge deposition from one particle. You are representing what would be seen on orbit. In a good day, what you would do is vary the LET at a heavy ion facility to create this curve of sensitivity of your device so that you can integrate it with the environment, giving you a rate. There are many ways to get at that rate, but for all intents and purposes, a rate calculation gives you a good understanding, good ballpark of how often you're going to see upsets. Here you can see the prediction from ground-based testing versus upsets in the two FPGAs that were on their way to Mars from JPL. You can see the errors accumulating randomly in time here. It's important to understand what I said before. Even things with very rare predictions, like here there was supposed to be one event every 300 years. That event occurred after 1 year of flight. It is random. So just because you have a rate that says once every 300 years does not mean you are going to live for 300 years, like the cumulative damage that we talk about. It's sometimes hard to communicate this to folks outside of our discipline, but it's an important point to make. As you get closer and closer to reality of your flight application, you can get more and more descriptive rates of what you're up against. We tend to be very bounding and conservative to allow for engineering trades to happen, but as we start to have more and more critical designs and softer devices, it's more important than ever that we test how we are going to fly. At least a representation of what you need the device to do. In this case, it's flip-flops in an FPGA. If I were to just use the cross-section of a flip-flop and multiply it by the number of flip-flops, I would see you have a much higher cross-section or device sensitivity that you are predicting versus if you were to take into account the system masking where you're actually testing that design itself. You can see the benefit that we achieve there. Let me think of how I'm doing on time. Okay. And so other ways of testing include subjecting devices to protons. What you're really doing with a proton test is you're hoping that you make secondaries that represent the LETs that you would see on orbit. And that's not really effective because it takes a lot of protons to make secondaries. Here you can see 3 little red dots. Here, going to an order of magnitude higher proton fluences, you can see 10 to 15 red dots, and then another order of magnitude to start actually arguing whether or not you've hit all of the different types of structures in a design. Naturally, those structures are repeated on silicon, but you're left wanting for more. The proton secondaries don't really make very high range particles. The particles in space have copious amounts of range. And so this is a strange proxy that people like to try to benefit from in terms of SEE testing, but the gold standard is still going to be heavy ions. Same thing with a board level test. You might not get all of the answers. If you put an entire board in front of a beam and it dies immediately, there's not much you can do with that information. But it is, as you add complexity to your test set, you are adding complexity to the level of abstraction of the information you can understand about physics of failure. And so there's typically an iterative solution to conducting a board level test that may result in going back and testing a part as is. And so just be aware that the board level test may not be the easiest way to get to the answers that you're seeking. It is important to understand your test setups, signatures, and what's normal operation and what are deviations from that. This can be very difficult when you're talking about things that draw a lot of current just in their typical use case. And here I'm showing a GPU where the latch-up event is just a deviation from the norm, and you have to know that it's occurring, and you have to know up against when you were subjecting the device to beam and what was going on during boot, during idle, during user interaction, all of those things. And so test before you even get to your experiment. Okay, so I'll breeze through a little bit of anomaly resolution. It's important to know the time and location of where you were and the previous history of the anomaly occurring if you've seen it multiple times. And you really want to know any recent changes to the vehicle operations or software changes that were uploaded. It's easy to want to blame the environment, but look to your design first. Radiation effects relies on the idea of that environment I was describing before. And so the L shell values, the magnetic field strength values, are particularly of interest in determining whether or not the anomaly can be attributed to the radiation environment. We watch, the big question is whether or not a solar particle event had occurred at the time that you saw the anomaly. And so there are GOES proton flux data available to the public. There are warning limits that are sent out. Here I'm showing a radiation storm where the proton 5-minute data exceeded this particles per centimeter squared per steradian. The 10 MeV protons exceeded that limit. That's when NOAA would send an email alert out to folks who are interested. Anyone has access to those emails if you need them. Here's an on-orbit example where we were commissioning Landsat 9. They were using flash memory. They needed flight software changes because they were seeing Cepheids that resulted in readback errors in the blocks out of the solid state recorder. So you saw this regular pattern of bad addressing in the image, and this was released in the public domain. Eventually they were fixed after we saw some additional B-side errors to the radio and getting resets. Again, things that were predicted to be very rare, but were realized during commissioning because we are in solar maximum right now. So the environment was acting up, but we did eventually get to fixing this, and the Cepheid problem was resolved for good data that's coming out of Landsat 9 now. In order to attribute that to the environment, there exists a tool that's available on CCMC through NASA that helps you step through the pragmatic decisions of whether or not radiation could have been what caused it. And so it asks you what L shell value you're at. And if you're, if there's a solar proton event in progress, yes, investigate SEE. If there's not a solar event in progress, what altitude are you at? Are you in the South Atlantic anomaly? If you're not, could you be in the transient belt slot? Could there be a geomagnetic storm going on? All of these things allow you to understand whether or not SEE are probably likely. And if SEE is not likely, then you need to go back to your design and understand that it's not SEP, you're not in the SAA, you're not in the slot belt, and if you don't have a history of being sensitive to very high energy galactic cosmic rays in the part, if your test data suggests that it's not susceptible, then SEE is very likely. But even though you might be having some weird activity in the environment, you need to go through this flow to understand if it's really radiation or not. And this is super helpful in determining that. Similar flow diagrams exist for spacecraft charging. Paul O'Brien from the Aerospace Corps put that together with a great team. And so I really think everyone should take a look at the links and tools that will be provided with the package that we've put together here. Yeah, these tools are everywhere. This is an emerging area of active and evolving research. We are steadily upping the ante of space weather data that is taken and integrated back into our tools. And so it's absolutely fascinating to see how fast this grows. I will get to closing with some of the common pitfalls. Thinking radiation is one number to meet. It's constant that I hear people saying, it's a 10 kilorad mission, you don't have to worry about it. But that is not the whole picture. There are many different susceptibilities and physics of failure that can occur. And anywhere that you have tight tolerance in your application, whether that be timing, whether that be parametric decisions of current or voltages that have very tight tolerances, that's where you want to pay attention to where deviations from radiation could occur. Adding tons of complex mitigation is really going to make the problem worse. You want to keep it very simple. And you don't want to forget about the other environment-driven failures like charging or corrosion or even temperature sometimes gets overlooked as where your problems are coming from. And last but not least, when folks claim heritage, that their spacecraft bus has flown for this number of years, if they add up all the missions that they supported, it's simply not true in terms of supply chain risk management of the devices that are within the build. Even if you are building to print, you are not getting the exact same devices that are flying right now. And so radiation can highlight some of the things like part-to-part variability or lot-to-lot variability that you might not anticipate. And so heritage is a very hard and difficult claim to make, particularly in the one particle effects, because as I said before, you could have an entire year in low Earth orbit where you didn't see a particle of a given energy. And then the first day you are at the moon, you see copious amounts of particles with that energy. And so a lot of people are wanting to take their successes in LEO and turn those into lunar surface missions, things like that for electronic systems. And it's a hard bargain, and it's hard to communicate across disciplines, the real risk that they are taking on, but something to keep in mind. So there are tools out there that are free. Like I said, this package will be provided. I encourage everyone to take a look at these tools for some basic modeling principles and understanding of the radiation problem set. And with that, I'll just say thank you and hopefully have some time for questions.
Okay, thank you very much, Mike, for a wonderful presentation. That was very informative. Let's go ahead and start reviewing the questions that we received. So first one is, are destructive events influenced from higher LET interactions, or is it more device specific?
It in fact is more device specific. So each device, let's just say you selected two different devices. They will have an onset of where they are susceptible to a given failure mode. So you may have a device with a very, very, very high onset for something like single event latch-up. And all it takes is one change to that die's mask set to put two transistors closer together, and that changes the onset of that effect. So the answer, and this is the classic one of radiation effects, is it depends.
Okay, great. Next question is, are there good resources to understand how up-to-date radiation models are? For instance, there are visibility into new model development for trapped particles or for GCRs and how this may affect radiation hardness in the future.
Yeah, absolutely. There's entire communities of practice. The workshop or meeting that has been supported by NPSS is called Seesaw, and it is, I'm not going to remember what the entire acronym is for, but it is a every other year meeting that occurs where the latest and greatest models of the space environment are pitted against one another, compared and contrasted, and emerging techniques and new data are incorporated. Um, a lot of the links that are shared here can point you to aggregate tools that pull a lot of environment models into one place. um, you could think of each environment contributor as a niche of its own. There are people who study the trapped electrons, the trapped protons, the galactic cosmic rays, and create models of them, and work towards understanding the science of each of those things' origins. And so, yeah, there are references upon references and rabbit holes to go down. But where we aggregate for engineering disciplines tend to be where there is consensus and buy-in of the engineering model doing what we need it to. And so those updates, albeit maybe slower than what's most available, are usually brought together.
Okay, great. Next question is, you've listed effects from electrons, protons, and heavy ions. Why don't we worry about neutrons in space?
So we do. I didn't mean to lead you astray, but if you are not dealing with a particle that has charge, it's not going to get trapped in a magnetic field. And so the populations in the Earth orbit are dominated by the charged particles that are in the radiation belts. And galactic cosmic rays are nucleus of atoms, but that's not to say that neutrons don't exist. It's just folks like the FAA and people who are talking about terrestrial radiation deal a lot more with neutron because of the galactic cosmic rays interaction with our atmosphere. It creates cascades of neutron showers, and so a lot of radiation from neutrons is actually because it is a secondary, and you have to have material that you're interacting with to have those neutron spillations occur. And so, for all intents and purposes, the neutron flux is fairly low in interplanetary space.
Okay, great. Yeah, so that takes us to the current end of the queue for questions that we have, but we still have a few minutes left in this session, so we should continue the conversation. So I have a couple of questions here that um, might be good to talk through. Oh, I see that actually Brian just submitted another question. Can you discuss more about the cluster sites on slide 21?
Yeah, I can actually, let me get back there. Hopefully it won't take too long. Had a lot, a lot of slides for you all. Um, 21, there we go. Um, so you are going to have different displacement damage processes in different materials because the lattice of that regular material can actually inform what these point defects and clusters look like. For me, the main material that semiconductors use right now, and that's not always going to be true for the future, is silicon. And so we have a long history of modeling the interaction of an incoming particle hitting a nucleus of the lattice and displacing it from its original location. Uh, Whether or not you have nuclear and elastic things depends on the incident energy of the particles. And so here you see 6 to 10 MeV, you start transitioning into that nuclear and elastic interaction. And that's really where you see the beginnings of these damage sites where Now you've created a secondary that may have its own decay, or you may be breaking apart one of the molecules or atoms that is part of the lattice. So now you're creating a vacancy, but you're also creating different particles that are interacting with the material themselves in different ways, creating electrons, creating delta rays, creating point defects everywhere that they go. And so as you go up in energy, the interactions and those secondary interactions of damage occur more and more and in a wider track structure. And so a lot of modeling, high fidelity, finite element modeling goes into understanding and picturing what those kind of things can happen. So here the red is the primary knock-ons movement. The blue is the secondary knock-on atoms. So your incoming particle hit the lattice. That particle's moving, it hits another particle. Those particles moving hit more particles, and you have these cascades of effects that are happening with the recoils. Deeply studied from I would say the 70s onward. There are a lot of references and resources that I can point you to. But this work from Cheryl Marshall, who was in my group for this short course that we have access to through IEEE, is a seminal paper to explain some of what's going on. And more recently, Goddard Space Flight Center has been working on what this means for commercial imaging systems, these type of defects, because you can actually create things that are unstable or can show up at the system level as random telegraph noise in hot pixels that blink on and off. And we see this in some of our modern day detectors, where these clusters are actually temporal, and charge can migrate in, get trapped, move out, and you're really just changing the material properties that you see. I hope I'm not answering your question, but opening up the conversation and understanding. In terms of optical materials, yes, this is what leads to darkening. This is what leads to color centers. But in semiconductors and active devices, this leads to many other things in terms of the physics of failure.
Excellent. Thank you very much for that answer. Let's see. One question that I had for you, Mike, is what role does the collaboration with industry and academia play in advancing RHA methodologies at NASA?
Yeah, it's absolutely crucial. And so to date, through my career, I have always collaborated with device manufacturers and other government agencies through my group in order to test things that look like promising candidates for future spaceflight, whether that be driven by design needs like, nuclear propulsion, driving the need for very high voltages, driving us to need things like wide bandgap materials to accommodate those voltages without failure, or if it's just common sense where things like digital logic need to be lower and lower power to save on battery and lifetime. It is those design needs that drive us to want to use the commercial electronics that change and grow and innovate much faster than the radiation hardened electronics of yesteryear. So at the beginning of my career, it maybe was like one or two commercial devices integrated in the design in a smart way. Now it is entirely full-on commercial builds of entire subsystems and learning how to take on those risks that is the job. And so it really leverages off of the partnerships that we can make. And I was trying to mention that, I think, when I was talking about the difficulty of assuring something that's complex. The manufacturers of devices that have spaceflight end users as customers do their own testing. We do independent verification tests of what they find. And this is very preliminary, but our partnerships allow us to flow information back and forth to one another. In the best of cases, we are informing that manufacturers change to their process and building of devices to accommodate for radiation effects. But in most cases, we're just looking at their roadmaps and letting them know our perceived demand, which they appreciate, right? We are never going to have the sort of pull in commercial electronics that terrestrial use cases are going to ask for. There's a million laptops a day, and there's maybe 10 spacecraft in a year, right? And so the number that we are going to procure is very low, even if they increase the price per part for things that they've worked on for spaceflight. We look at previous process and feature sizes performance to have a sort of line in the sand of whether or not a new offering is going to be worse or better. But it is this question of, is this technology feasible? When we go to 3 and 5 nanometers, is it feasible that we could put something like that into space? And if the answer is maybe, through our partnerships, then it is trying to understand with the design community whether or not the benefit of that technology can be realized. Like, if you need it for its low power, but you are also needing it for the high speed type of clocking that you are trying to get a lot of data throughput out of, that high speed clocking may be a driver for the radiation response. And if we didn't test with a manufacturer in advance, it would be too late to do anything about it. But we can, once we have a customer who's talking about flying it, whether or not they're fully funded or not, if they're at a proposal case, we could start to look at the corner cases and the worst case conditions in their application. And ultimately, then we can just architecturally demonstrate what's going on. Now, when things get really, really complex in terms of like something like a system on a chip, you just turning it on, you're already demonstrating an architecture because so many things are going on. And you just have to build awareness of what is it your designers are going to use it for. And finally, system assurance comes whenever we start doing rates for that environment, knowing the concept of operations, like, is it only used whenever you're commissioning? Is it only, is it turned on once and then it's left on for the entire mission? Those kind of questions get answered when you actually have a use case. And that's where we get to risk quantification and finalizing the testing for system assurance. I hope that helps answer the question.
Yeah, certainly. Thank you
Yeah.
very much for answering all of those questions. I think it was an incredibly engaging discussion. So it is time to conclude the final presentation of this session. Thank you again very much to both of our speakers, Mike and Brian. As a reminder, any questions that you do have that were not answered today will be addressed by email. Following today's webinar, all registrants will receive an email from EMA with a link to the recording of this presentation, as well as a copy of the presentation. If you have any questions about a particular section of interest to you, please feel free to reach out either through the ema3d.com website or reply to the aforementioned email. Next up, please look forward to the upcoming keynote address led by Senior Director of Product Management, Jim Delap from EMA's technology partner, ANSYS, focusing on the future of electromagnetic simulation, which will begin today at 1 p.m. Mountain, 3 p.m. Eastern. Thank you all very much for your time and attention, and I hope you have a great rest of your day.